Now we look at this set of equations. First equation is the same as it was here. Second equation is not quite the same because I changed the sign of my 8y. And if you think about it, what's that going to do to the slope? Well, that's going to give you a positive slope because you subtract 4x from both sides, then divide by -8, you're going to have a positive 1/2. So the slope's going to be positive 1/2 instead of -1/2, meaning the graph's going to be going up and not down so that the two lines will intersect. Now let's see how that works out. I've written the augmented matrix. We can do the dotted lines, but I kind of don't write them after a while. And now we're going to do the same operations we did before because that will have the effect of eliminating x. So if I do that here, first equation minus 4 times the second, that's going to eliminate x. That's going to give me 0. And then it's going to be what? -4 times 2y is -8y. Added to -8y gives me -16y. And that's going to be what? Well, -4 times 4 is again -16, just as it was over here, added to 24. That's going to give me 8. Okay, so what am I going to get down here? Well, in this equation, of course, I could just write down the numbers that we get here because we know that this operation has to give us something that's compatible with something that's consistent with this, and the only thing would be that. Okay, but let's just go through it again. -4 times 1 is -4, added to 4 gives me 0. -4 times 2 is -8, added to -8 gives me -16. And -4 times 4 is -16, added to 24 gives me, oh, I keep putting it right, that's 16, gives me 8. Okay? Now, we're trying to find a solution to this equation. Over here, we never had a single solution. We never got to a single solution. In this case, we got to an incompatible, to an impossible set of equations and realized there's no solutions. Remember, that corresponded to lines that were parallel but didn't intersect. Here, we completely got rid of the second equation, which just left us the first equation, which is the equation of a straight line, so that our entire solution is just that one straight line, corresponds to that one straight line. Any value of x gives you a value of y. Any number for x gives you a number for y. Any number for y gives you a number for x. So there are infinitely many numbers that we could put in for either x or y. So we have infinitely many solutions. And they all correspond to that straight line. Okay, what do we have here? What's this mean? Well, we've already given it away. The lines aren't parallel, they intersect. But let's see how it works out. Okay, we want to complete the solution. We want to find what y is, and we want to find what x is. So, well, we can write x plus 2y equals 4. In this equation, just reduces down to 0x, which we don't bother to write down. Y equals -1/2. Okay, so we're not sure what the x is, but the y coordinate of the intersection point is -1/2. Okay, now what did we do here? We multiplied this equation by -1/16, didn't we? So what we did was we wrote down the first equation, and then we wrote down -1/16 times the second equation. Incidentally, I wrote this wrong. I should have written 2 here. Hopefully you picked up on that. This is equation 2, and we're subtracting 4 times equation 1. Okay, so hopefully that didn't cause you a great deal of distraction. Okay, we have then, if we do the same thing here, we have 1, 2, 4, and then -1/16 of 0 is still 0, -1/16 of -16 is 1, and -1/16 of 8 is -1/2. So, same thing done to the equations can be done to the matrix, and we have what we have. Okay. The augmented matrix is still the augmented matrix for the corresponding system. Now we still need to solve for x if we want to find our point of intersection. There are various ways we can do this. This augmented matrix is in what we call upper sort of, well, the matrix we have for the first two columns is in what we call upper triangular form. So this is the upper triangular form of the reduced matrix. And upper triangular just means you have a diagonal here, and everything below the diagonal has to be 0. I can take the fact that y equals negative 1/2, which is exactly what this equation says, plug that in here for y, and solve for x. And that's very easy to do. 2 times negative 1/2 is negative 1. If I add 1 to both sides, I get x equals 5, and now I know that my intersection point is where x equals negative 5, y negative 1, x equals 5, y equals negative 1/2. The intersection point is the point 5, negative 1/2. Now I just said that, but I need to write it out because in the first place, you probably didn't hear everything I said, probably went by you quickly. Although if you really know this, then you could have solved this in your head equally easily, and you did understand what I said. Either way, okay. So now, as far as adding multiples of rows to other rows, rather than just plugging in y equals negative 1/2, that's not an operation we can do to manipulate the equations in the way that we're manipulating them. We know that that'll work, and that's an important understanding. When you get to this point, you can always use this process, which we call back substitution. You take this value, you back substitute it into this equation, and you can get this value. And if you've got a whole series of equations in upper triangular form, you can just keep back substituting the values that you've found and solve for all your variables. Okay, but for this particular situation, here we have it. What we can do is we can add negative 2 times this row to this row. That'll eliminate y and tell us what x is. So we're going to do negative 2 times row 2 plus row 1. Or negative 2 times equation 2 added to equation 1. Okay, well, negative 2 times 0 is 0, so we add 0 to x, and that doesn't do anything. We still have x, which is a good thing because that's what we want. And we have then negative 2 times y is negative 2y added to 2y gives us 0y. And negative 2 times negative 1/2 is 1 added to 4 gives us 5. And we still have this one, and we could have written the 0x. Okay? 0x plus y equals negative 1/2. Now, with the rows of this matrix, we're doing exactly the same thing. We're just not writing down the x and the y and the equal sign. But we know what each row stands for. Okay? Negative 2 times the 0 plus 1 gives us 0. Negative 2 times the second row, negative 2 times 1 is negative 2 added to 2 gives us 0. Did I say this gives us 0? This gives us 1. I'm not sure I said that right. And then negative 2 times the negative 1/2 gives us 1 added to 4 gives us 5. And our second row stays the same as it was. So either way, x equals 5, y equals negative 1/2 is our solution. And our graph will reflect this solution. Now if we graph things, we don't necessarily graph them exactly enough to tell exactly what the solution point is. But let's just graph these two equations here. Well, this equation is the same as it was before. We have intercept 0, 2, and 4, 0. Here's our first equation. And our second equation has x-intercept. Well, let y equal 0. You find that the x-intercept is 6. And the y-intercept, if we let x equal 0, you get y equals negative 3. So we go down 1, 2, 3. So there's our intercept. And our line, I hope I can hit it because I'm kind of a bad angle. That came close enough. Get the idea. Okay, here's our intersection point. So here's our second equation. Here's our intersection point. Okay. Now, could that possibly be at x equals 5? Well, this point was 4, 0. This point is 6, 0. This looks like, actually, the way I've graphed it, it looks maybe a little closer to 6 than it is to 4, but it turns out to be halfway between. And it's a little ways below the axis. It's very plausible that that's the point 5, negative 1/2 that we get here. Now, look at the augmented matrix in this case, the augmented matrix in this case, the augmented matrix in this case, the reduced augmented matrix. Okay? What can you say based on the reduced matrices? Okay, we'll talk about that and kind of summarize in the next clip.